on A-infinity structures.
Thank you very much. So in this directory, you will find notes and references like last time. And well, let me start with a reminder. Yes, let me share my screen. Okay, so let's start with a brief reminder. Yes.
I guess we can start the recording as well.
Yes. Okay, so let me start with a brief reminder of what we saw last time. We saw the definition of A-infinity spaces and A-infinity algebras. Let me quickly review that. So A-infinity spaces were defined as abstractions of loop spaces. So an A-infinity space is a topological space Y, which is endowed with higher composition maps, n-ary composition maps for each n greater or equal to 2. And these composition maps are parameterized by the points of the nth Stashev associahedron Kn and have to satisfy certain compatibilities. And one also assumes the existence of a strict unit, more on that later. So the compatibility conditions are dictated, if you like, by phase inclusions among these Stashev associahedra. Yes, for example, if you look at K3, which is just an interval, it has a boundary made up of 2 copies of K2. And then K4, this pentagon, which parameterizes 4 array operations, has a boundary made up of 5 copies of K3, and we have to have suitable compatibilities between the operations when we restrict to boundaries. Okay, I haven't been very precise on that. I mean, the precise formulation would be to use, or a convenient way to give a precise formulation would be to use operads, but we won't need this. Yes, let me also show you again the picture of K5, the 3-dimensional Stashev associahedron. So here I have indicated the binary trees corresponding to some of the vertices, and I was asked, well, so these pentagonal faces are of course copies of K4 of this pentagon. Yes, so they appear in the boundary of K5. And but this is not pentagonal. So where does it come from? Well, it comes from this situation. Yes, if we look at this binary tree, yes, we look at the orange branch here, and you can see the orange branch remains the same throughout the process. And the yellow branch, if we move the yellow branch from right to left, that is here, and then we move the blue branch right to left. And here, on the other hand, we first move the blue branch from right to left, and then we move the yellow branch from right to left. Yes, and these two homotopes are completely independent of each other. They're separated by this orange branch, and this independence reflects itself in the presence of this square. Okay. Now, if we want to pass from A-infinity spaces to A-infinity algebras, we use the reduced singular chains functor. So let's fix a field K. Then an A-infinity algebra, well, so that's the notion which we get then. It's a graded vector space endowed with graded maps, homogeneous K-linear maps, Mn, defined now for all n greater or equal to 1. There's a small difference with the topological case. They have dimension 2 minus n, which is minus the dimension of the nth Stashev associahedron, and they satisfy compatibility conditions. Well, first of all, M1, which is of degree +1, is a differential. So MA becomes a complex when endowed with M1. Secondly, M2 is compatible with M1. Yes, if we, so one way of saying it is that M2 is a morphism of complexes because this is nothing but the differential of the tensor square of A, of the complex A with M1. So this equality just says that M2 commutes with the differential. Another equivalent way of saying it is that M1 is a graded derivation with respect to M2. Yes, here we first multiply and then we apply the derivation. And here on the right-hand side, you recognize the Leibniz rule. Yes, you first you apply the differential to each of the arguments and you multiply. Yes, so these are two equivalent ways of seeing this equality. And now for n equals 3, it becomes a bit more interesting. We have this equality. Well, so first of all, the left-hand term, if we evaluate the left-hand term on 3 elements of degree 0, then as you can see, we get the so-called associator. Yes, the failure of associativity for star. Yes, I write star instead of M2. And well, what do we get on the right-hand side? Well, if you look at this, this is again nothing but the differential of the tensor cube of A with M1. So what we get on the right-hand side is just the boundary of M3. M3 is homogeneous of degree -1, and its boundary in the morphism complex is precisely this expression. And okay, so now let's establish the link with the topology. Yes, so here on the left-hand side, we have, if you like, the difference of these two binary trees, which are 2 copies of K2. On the right-hand side, we have, well, so these 2 copies are the boundary of K3. And well, since this element is the boundary, the algebraic boundary of M3, it's natural to associate M3 with this interval, with this top dimensional cell in K3. More generally, we will always, the top dimensional cell of the nth star-shift associahedron will always be associated with Mn. And then it's natural to label this interval with another tree. Yes, now it's no longer a binary tree, it's here a tree with 3 branches growing out of the root, yes, corresponding to the 3 inputs of M3. Okay, now if we go 1 dimension higher, I didn't write this out last time, but if you take the general equality and specialize it to n equals 4, you get this, which you can write again in the same form. You have a certain expression, quadratic in M2 and M3, which is equal to the boundary of M4. So again, it's of very similar nature. Yes, you can view this expression on the left as a higher associator, which is the boundary of M4, or in the topological setting, the boundary of the 4th star-shift associahedron. Yes, the 4th star-shift associahedron was this pentagon. Yes, and now we can label, now that we have introduced these more general trees, we can label the boundary of the pentagon with these trees, which have M2 and M3. And these 5 intervals of the at the boundary correspond precisely to these 5 terms in the higher associator. And the fact that it's the boundary of M4 corresponds to the fact that, well, this pentagon is the boundary of the solid pentagon. Okay, and this goes on in higher dimensions. We can, so last time I wrote this equality by writing a whole sum equal to 0. Now I have separated the sum into 2 parts. The boundary of Mn, and then a sum of quadratic expressions in the Ms and Mu, where S and U are strictly bigger than 1 and strictly smaller than n. Yes, so you can always write it like this. And like this, it is perhaps more similar to the topological situation. So this is the higher associator, and like in this case, it corresponds to the boundary of the Star-Sheff polytope. Okay, and this is the end of the reminder. So now we start with the second chapter, if you like. Okay, let me try to find my notes. Yeah, a lot of windows on this desktop. Just a moment. Yes, the chat window is now. Yes. Okay, so let me switch to Blackboard mode. Yeah, so in this section, we will see minimal models, the definition of morphisms of A-infinity algebras, which is non-trivial, two notions of unit, and then at the end, the notion of A-infinity categories. So let's start with minimal models. Perhaps you remember the second motivating problem from the first lecture. The second motivating problem was to reconstruct a category of filtered modules from a Yoneda algebra. So let's recall this setup. We take B concentrated in degree 0, an ordinary associative unital algebra, and we take some B module. In the motivating problem, it was the sum of B modules M1 up to Mn, and we were interested in the category of modules filtered with subquotients among the Mi. And the claim was that this category is controlled by the Yoneda algebra with an A-infinity structure. Okay, so we need to put some A-infinity structure onto the Yoneda algebra. Okay, so the claim is that this Yoneda algebra of M with itself has a canonical A-infinity structure. Yeah, I'm exaggerating a little bit. It's almost canonical structure, such that M1, the differential, vanishes, and M2 is the Yoneda product, the ordinary product of extensions. Okay, and to see this, let's first recall one of the possible definitions of this Yoneda algebra. So we choose a projective resolution of M. A complex P, right bounded and quasi-isomorphic to M, concentrated in degree 0. And then we consider the differential graded endomorphism algebra. So this is the Hom complex, Hom dot over B from P to P. So first of all, this is a complex. Yes, it's defined in the same way as Hom dot over K. The nth component is the space of homogeneous maps of degree n not necessarily compatible with the differential from P to P. And this morphism complex becomes a DG algebra in a natural way. Yes, we endow A with the multiplication mu, which is just the multiplication of graded maps. And I have to, okay, yes, with the multiplication mu of graded maps. Okay, and then A together with the differential and with this multiplication becomes a DG algebra. Hence an A infinity algebra where all mn's for n greater or equal to 3 vanish. And the homology of A, okay, by one of the possible definitions of the Yoneda algebra, this is the Yoneda algebra. Okay, so we're claiming that if we have such a DG algebra, then we get an A infinity structure on its homology. And this is, in fact, a special case of a more general theorem, which states that if we have an arbitrary A infinity algebra, we get its homology inherits an A infinity structure with vanishing differential. So this is a theorem first proved by Kadeishvili long ago in '82. Namely, yeah, so I should say that this is a special case. So now the claim that we have this A infinity structure is a special case of Kadeishvili's theorem, which says that if we have an A infinity algebra A, okay, then its homology carries an A infinity algebra structure such that M1 vanishes and M2 is just the multiplication induced by the multiplication M2 of A. And secondly, there is a quasi-isomorphism, an A infinity algebra quasi-isomorphism between the homology of A with its A infinity structure and A itself, which lifts the identity of homology. Yes, yes. I mean, on the left-hand side we have vanishing differential. So the homology on the left-hand side is just again H star of A, and the homology on the right-hand side is H star A, and we require that this A infinity algebra quasi-isomorphism should induce the identity when we pass to homology on both sides. Okay, and this structure not only exists, but it is unique. Moreover, this structure is unique up to non-unique. infinity algebra isomorphism. Yes, so if you like, it's the same type of uniqueness as you have in a minimal projective resolution. You have uniqueness up to isomorphism, but the isomorphism itself is not quite unique. Okay, and so here I have been using the notions of A infinity morphism and quasi-isomorphism. These are non-trivial notions, and I will define them in a moment. Of A infinity algebra morphism and quasi-isomorphism will be defined in a moment. Yes, they are a bit long. And well, let's look perhaps at an example. First, a bit of terminology. We say that an A infinity algebra is minimal if its differential vanishes. Okay. And in the situation of the theorem, the homology with its minimal A infinity structure is called a minimal model for the A infinity algebra A. In the situation of the theorem, A infinity algebra H star A is called a minimal model of the A infinity algebra A. Okay, so let's look at a simple example. Let's take an algebra B as in the motivating problem, be given by the following quiver with relations. We have three vertices. We have arrows alpha, beta, and gamma, and we impose the relation alpha, beta, gamma vanishes. Okay, and then it is not hard to determine the minimal model of the Yoneda algebra with the minimal model A infinity structure. Then next, so here we take M to be the sum of the simple modules S1 up to S4, concentrated at the four vertices, and then the Yoneda algebra with its minimal A infinity algebra structure is given by, again, by a quiver with relations and higher multiplication. Namely, yes, we just, of course, the vertices remain the same. Yes, and then we have this is the X quiver dust. Yes, we have extensions A, B, and C of degree 1. So these are the elements, the 1 extensions corresponding to the arrows. And then we have another arrow E, which corresponds to the 2 extension. It's in degree 2. And the all, well, non-trivial, so I accept the products with the idempotence associated with the vertices, so the non-trivial products vanish. In particular, the products CB and BA vanish, except one M3 product, namely M3 of CBA equals, okay. And well, it is not hard to compute this. In general, there are several methods for computing minimal models. Yes, I remark. How do we compute minimal models? There are at least, well, I'd like to mention 2 methods. One method is very classical. It's called homological perturbation theory. And this is explained in Appendix A of the notes. Yes, there is a very nice reformulation of the construction in terms of trees due to Kontsevich-Solomon, and you will find this description in terms of trees in the appendix. And then there is another method which can be used, for example, for this example, which we have just seen. So the example above is best computed by another method, which is explained in Appendix B. Yes, so this other method, let me just tell you what the idea is. You use that B is quasi-isomorphic to the following DG path algebra. Yes, so what do we take? Well, we take the same quiver. 1, 2, 3, 4, A, B, C. And then we take, instead of the relation, we add another arrow, F of degree -1, whose differential is the relation. So E is a new arrow of degree -1, and it has a differential which is equal to the relation. And then it is more or less clear that the corresponding differential graded path algebra is quasi-isomorphic to the algebra B, which I defined. And then it is very easy to read off the Yoneda algebra with its infinity structure from this DG path algebra together with its differential. So the differential fully encodes, this differential fully encodes the higher structure. Yes. Yeah, this is explained in Appendix B. Okay, now some more terminology. Yes, let's say definition. We say that an A-infinity algebra is formal, if the higher multiplications vanish and the differential also vanishes, as if n equals 0 for n equals 1 and n greater or equal to 3. Yeah, sorry. Well, if there is a minimal model with these properties, yeah. Yes, yeah. Sorry. If there is a minimal model, if it admits a minimal model, well, so by definition, M1 vanishes, and we require that Mn vanishes for all higher n's. Okay. And a graded algebra is intrinsically formal. Yeah, this is somehow the best situation. And one really has to say if it admits a minimal model, because the property of having vanishing higher multiplications is not invariant under A-infinity isomorphism. So there may be minimal models which have non-zero higher MNs and others which have all higher MNs equal to 0. And the definition of formality is that there is some minimal model where they vanish. Okay. And then we say that a graded algebra B is intrinsically formal if whenever we have an A-infinity algebra whose homology is B, this A-infinity algebra is automatically formal. So just by looking at its homology, we can see that it is formal. Okay, yes, so if each A-infinity algebra A, which has homology isomorphic to B as graded algebras, is formal. Okay, well, this is of course the nicest situation. You can get rid of all the higher multiplications without doing any computation. Well, if you already know that your homology is formal, and there is a nice sufficient condition for intrinsic formality due to Seidel and Thomas. From 2001, namely, if well, suppose that our graded algebra is augmented. So we have, there is a graded algebra morphism epsilon from B to K, which composes with the unit as the identity. Okay. Then, if bigraded Hochschild homology vanishes in degrees n and n2 minus n, in bidegree n minus n, 2 minus n, then B is intrinsically formal. Yes. And so here these spaces are bi-graded Hochschild cohomology spaces. And since B is graded, Hochschild cohomology becomes bi-graded. The total degree is 2, yes, which is quite natural. Okay, so this is a possibility which sometimes allows to show formality. It's also important to detect non-formality. And to detect non-formality, one can sometimes use messy brackets. Yes. So-called messy brackets. Okay, suppose for simplicity that A is a DG algebra. And we have 3 homogeneous elements, 3 classes, U bar, V bar, W, homogeneous in homology, such that U bar, V bar vanishes and V bar, W bar also vanishes. And then we choose A and B such that UV is the boundary of A and VW is the boundary of V. So if you like this, the situation is like this. UVW, and then the composition UV vanishes in homology because it's the boundary of A, and the class of the composition VW vanishes in homology because it's the boundary of B. And then, if you like, the triple composition vanishes for 2 reasons. The first reason is A, and the second reason is B. And the difference of these 2 reasons is a cycle. And the class of this cycle in a certain quotient is the value of the messy bracket by definition. So the messy product UVW is the class of the difference between the 2 reasons, A composed with W minus -1 to the degree of UB in the quotient H upper star A modulo U bar H star A plus H star A times W bar. Yes, this is just a vector space. Okay. And well, why does so I claim that non-vanishing of such a messy product yields non-formality of the algebra. Well, the fact is that this class will always equal the class of M3 applied to U bar, V bar, and W bar for any choice of minimal model. So this class equals the class, well, at least up to sign of M3 applied to U bar, V bar, W bar for any choice of minimal model of A. And so if this is non-vanishing, then of course A is non-formal. So A is non-formal if this class is non-zero for some u bar, v bar, w bar, but which have to satisfy the condition. Yes, it's not defined for all triples of classes. You have to have this vanishing conditions. Okay, and now I think it is time to say what morphisms are. Let me see. Well, yes, maybe, yes, sorry, I should have made a short break about 13 minutes ago. Well, maybe I can make it now before we come to morphisms. Let's see, are there questions? Yes, let's see. There was a whole discussion. What is the definition of A infinity? Yeah, I will give it. I will give it now. M2 is automatically associative. Absolutely, yes. And what is N in the theorem of Seidel-Thomas? N is to be, yeah, sorry, it's any n greater or equal to 3. Yes, yes, yeah. So yeah, sorry, we need to assume this for all n greater or equal to 3. Thank you. Okay. And then I said that H upper star is a minimal model for A. So in general, a minimal model would be a minimal A infinity algebra, which is quasi-isomorphic to A. Yes, that is true. No. So the general notion is it's an A infinity algebra, A infinity quasi-isomorphic to A. Yes. Are there more questions? Okay, then let me come to morphisms. So this is, I think, yes, this is 2. Okay, let me define what a morphism is. A morphism f a b of A infinity algebras. Okay, it's not a map which commutes with everything, but it's a sequence of graded maps. There's a family of graded maps Fn on the nth tensor power of A to B, defined for all n greater or equal to 1, which are homogeneous of degree 1 minus n and satisfy the following conditions. F1 composed with M is M composed with M1 composed with F1. So F1 is just a morphism of complexes. Okay. then F1 composed with M2 equals M2 composed with F1 tensor F1 up to a correction, namely M1 F2 plus F2, and then the differential of the tensor cube. Okay, and so again, yes, so this is just this correction term is just d of F2 in the morphism complex from the third tensor power of A, sorry, the second tensor power of A to B. Yeah, sorry, there are too many factors here. M1 tensor 1 plus 1 tensor M1. And then, so F1 commutes with M2. M2 up to a homotopy given by F2. In particular, in homology, F1 induces an algebra map. And then, more generally, the nth condition we have the following condition. Yes, so we take the sum over minus 1 to the r plus st of fu composed with 1 tensor r tensor ms tensor 1 power t, and this should be equal to the sum over all decompositions of n into positive integers i1 up to ir minus 1 to the s of mr composed with fi1 tensor fi r, and for s you can look at the notes. The sign. Yes, so the picture for this identity is as follows. Yes, we take some string of arguments on the left-hand side, then we apply higher multiplication ns to some of them, and then we apply fu to the result, and this, the sum over all possibilities should be equal to the following. Well, we take the same string of arguments and we break it up into pieces, and to each piece we apply some fi. And then we apply mr to the result. Of course, this mr is in the algebra B and this ms is in the algebra A. Okay, yeah, so it's, well, it's not so unnatural. And then let me continue the definition. We say that F is a quasi-isomorphism if F1 is a quasi-isomorphism. Yes, that makes sense. F1 is a morphism of complexes. Then we say that F is strict if all the higher Fi vanish, I greater or equal to 2. Then we have the identity morphism. It's the strict morphism F with F1 equal to the identity. And then we have the rule for the composition. Fg it's defined as follows. Yes. Yes, so it's again it's a family. We have to define its nth term. Okay, what do? Well, we take the same sign as before, and again we take the sum over all decompositions of n, and we compose Fr with Gi1, and so Gi. Okay, so we get a nice category. We obtain a category, and we will see that in this category, a nice category with a distinguished class of morphisms, namely the quasi-isomorphisms, and we will see that in fact each A infinity algebra is A infinity quasi-isomorphic to a DG algebra. So up to A infinity quasi-isomorphism, we don't really need A infinity algebras, just from some point of view. So why do we consider them? Well, we consider them because they arise in nature. Yes, they arise in Fukaya categories. That's one reason. And another reason is that they allow us to write smaller spaces. Yes, this DG algebra quasi-isomorphic to a given A infinity algebra is usually enormous, whereas the A infinity algebra, yes, for example, if it's minimal, its components really have minimal size, minimal possible dimension. Yes, of course, the multiplications are more complicated than for a DG algebra, but the spaces are very small. So they are actually useful for computations, and they arise in nature, and that's why we consider them. Okay, and so now, yes, there are 5 minutes left for the 2 last sections. So let me pass again to slides. Yes. Yes. So we have not spoken yet. Yes, so here you have the formula which we have just seen. And well, we have not yet spoken about units. There are several notions of units. I will present 2 of them. First, the notion of strict unit, which already appears in Stashev's work. Well, a strict unit is the strictest possible notion. It's an element 1 in A, which is a unit for M2, and which is such that the higher multiplications vanish whenever one of the arguments equals our unit. Okay, and then, yes, so the unit does not interfere in the higher multiplications. And then we have the natural notion of strictly unital morphism between strictly unital algebras. It's a morphism which takes the unit to the unit. And again, in the higher components, the unit doesn't interfere. The higher components of F vanish whenever one of the arguments equals the unit of A. And well, just a remark, if A is strictly unital, then as in the case of usual algebras, we have a strict A infinity morphism from K to A, which sends 1 to 1. So we have a unit morphism eta that will be useful in a moment. Now there is another notion which is somehow more adapted to practice, which is much weaker. Namely, we say that A is homologically unital if its homology, yes, with the multiplication by M2 is a unital graded algebra. And then we have the corresponding notion of morphism. Okay, now this looks much weaker, but it turns out that it is essentially equivalent. So fortunately, it is essentially equivalent. There is no essential difference between these two notions, yes. At least if you make the correct statements, yes. So suppose we have some homologically unital algebra, yes. So we have some homological unit. We might try to correct it into a strict unit, and that doesn't work usually. But we can find a minimal model. Yes. So if we replace our algebra by a quasi-isomorphic one, for example, a minimal model, then we can get a strict unit. Yes, so we have to change the algebra. Usually we have to change the algebra in order to make the unit strict. Now, so in this way, we can somehow reduce everything to the study of strictly unital A infinity algebras. And also, as far as morphisms are concerned, if we have two A infinity algebras which are strictly unital and some morphism which is only homologically unital, then we can deform it into a strictly unital one by a homotopy. And well, I haven't defined homotopy between morphisms of A infinity algebras, but I will do it next time. Okay. Yes, and then it's another useful, yes, so this is the story about units. And then we have the notion of augmentation, which is also often useful. It's defined in the same way as for classical algebras. And the notion of morphism of augmented algebras is also the natural one. And then as for usual algebras, yes, I don't know whether you have ever considered non-unital algebras, but it's a nice exercise to show that the category of non-unital algebras is equivalent to the category of augmented algebras. And this exercise still works in the A infinity world. Yes, so here you have the two quasi-inverse equivalences. And yes, so one advantage of an augmented algebra is that when we compute minimal models, we can forget about the unit. Yes, we don't need to bother with the unit. I mean, the unit is a loop. It's unpleasant, but we can just forget it if the algebra is augmented. Okay, and then one last section, we have the notion of A infinity category, which is the natural multi-object version of the notion of A infinity algebra. Yes, it has a class of objects. For any pair of objects, we have a morphism space, a graded morphism space, and then we have compositions, Mn. Now the compositions, well, they go from tensor products of morphism spaces to some morphism space. And they satisfy exactly the same relations, where we now have to interpret all the terms as graded maps from this tensor product of morphism spaces to this morphism space from x0 to xn. Yes, so it's the natural multi-object version. Like in the case of algebras, yes, the multi-object version of a K-algebra is a K-category. And then as an exercise, you can define A-infinity functors and strict and homological unitality for A-infinity categories. It's also augmentations. It works exactly the same way. Also, as in the case of algebras, if we have something concentrated in degree 0, a homologically unital A-infinity category concentrated in degree 0 is the same as a category, K-category with units. And similarly for functors. Okay. And then, well, there is one interesting notion which is not, doesn't make much sense for algebras. That's the notion of a quasi-equivalence, yes, which is completely analogous to the one we have for DG categories. We say that an A-infinity functor between homologically unital A-infinity categories is a quasi-equivalence if it induces quasi-isomorphisms between the morphism spaces. So its first component induces quasi-isomorphisms in the morphism spaces. And if we look at H0, yes, since we have assumed that our categories are homologically unital, H0 of A and H0 of B, yes, they have the same objects, but the morphism spaces are just the H0 spaces. And this is going to be a true functor between two categories. And we require that this functor should be an equivalence of categories. Yes, so this is the natural extension of the notion of quasi-equivalence between DG categories. And yes, so if our categories are concentrated in degree 0, then a quasi-equivalence is the same as just a K-linear equivalence. Yes, so this is the natural A-infinity extension of the usual notion of K-linear equivalence between K categories. And yes, so and this ends this second lecture. Yes, sorry for going over time.
Thank you very much for your talk. Yeah, and there are some questions in the chat, or maybe someone wants to ask more questions now.
At the chat. Yes, is there a way to better understand, memorize the plus-minus sign in the construction of A-infinity algebras and A-infinity morphisms? So there are two things. So next time I will introduce the bar construction, and the bar construction combined with the causal sign rule in particular explains all the signs. Yeah, so well, more precisely, the bar construction plus the causal sign rule plus one more convention explains all the signs. And so this additional convention is not unique. Different authors use different conventions, but yeah, so there's just this unique convention where you have to make a choice once and for all. If you do not, so there's a way of getting rid of most of the signs, and in particular of the signs coming from this convention, which is to shift everything by 1 degree to the left. But it's not always natural to do that. Yes. Okay, so we will see more, we will see the more precise answer to this question next time. And then, is there an analogous morphism of A-infinity spaces? Yes, there's an analogous notion of morphism between A-infinity spaces, absolutely, yes. And then, okay, then there are some compliments in Spanish. Thank you very much, Marta. Muchas gracias. And then there is like a vector space generating a free associative algebra. Is there a notion of free A-infinity algebra? Yes, there is such a notion. If you like, it's because A-infinity algebras are the algebras over some operand. So whenever you have a a notion of algebra defined by an operator, there is a natural notion of free object. However, well, a word of caution. So it's going to be free with respect to the category of A-infinity algebras and strict morphisms. Yes, so the morphisms which arise as morphisms between algebras over operands in this case are only the strict morphisms. So if we accept this slight nuisance, then there is a good notion of free A-infinity algebra. Yes, yes. And then I think there should be a notion of A-infinity quotient. Yeah, if you like. I mean, it depends on for what kind of objects. I mean, there is a at the level of A-infinity categories, there is a notion of A-infinity quotient, which is essentially the same as the notion of DG quotient. Yes, and you pass to the corresponding DG categories. If you look at algebras, well, you can define a kind of notion of ideal. I don't know whether this is very useful. I think I've never used this. And then, is there any geometric interpretation of morphisms between A-infinity algebras? Yes, yes, if you like, yes. I mean, well, so the morphisms will become natural once we look at the bar construction, and the bar construction. So the algebraic bar construction, which I will present, is the algebraic version of the topological bar construction of an H space. Yes. So in this sense, you can. It does have some geometric interpretation. Yes. Okay. Let's see. Are there more questions?
So you can just turn on the microphone and ask any questions if you, or maybe not any questions, but if you have any questions on A-infinity.
May I ask a question, Bernhard?
Please.
Thanks for the talk. So earlier, close to the end of the talk, you left a remark saying that every A-infinity algebra is in fact up to quasi-isomorphism of A-infinity. Quasi-isomorphism is a DG algebra.
Yes.
I was just wondering, because some of these definitions, such as minimality and formality of the A-infinity algebras, is quite new to me and pretty involved and hard to verify. I was just wondering if
yes.
They could be translated in terms of DG algebras in a more familiar language.
No. No, unfortunately, no. I mean, at least I don't see any. Yes, I mean, so you have these notions for A-infinity algebras, and in particular, you have them for DG algebras, and the simplest way to define them for DG algebras is to use the A-infinity language. I mean, okay, yeah, well, okay, yeah, for formality, yeah, sorry. Okay, for you can also define it in a more intrinsic way, if you like. A DG algebra will be formal if and only if it is linked by a chain of quasi-isomorphisms to its homology endowed with the zero differential. Yes, so you have this criterion, which is true for DG algebras, which is, by the way, also true for A-infinity algebras. Only in the case of A-infinity algebras, you can actually, instead of taking a whole zigzag, you can take just one morphism. Yes.
I see.
Yes, so that's one, yeah, one nice thing about the A-infinity formalism. When you have DG algebras, you need zigzags to describe morphisms in the localization.
Mm-hmm.
With respect to quasi-isomorphisms. When you look at morphisms between A-infinity algebras, as we will see next time, when you have an A-infinity quasi-isomorphism, then it is invertible up to homotopy. So yeah, so you can just, you don't need any zigzag
And may I possibly, as a follow-up question, ask if this A infinity quasi-isomorphism that you use in order to look at the A infinity algebra as a DG algebra, is that something like explicit, or is that written somewhere that we can look at?
There is a universal construction, and which gives a very big DG algebra. Yes. Yes. It's kind of an iterated tensor algebra. So tensor of tensor.
Thank you.
There are a couple of new questions in the chat, but maybe we should finish for the next talk to start.
Is there a theory? Is there a theory of derived algebraic geometry involving A infinity algebras? Yeah, maybe the next question is there an A infinity nerve functor? And the answer is yes. Yes. So the answer is yes. So for example, you can find such a functor in a paper by Giovanni Faonte in his thesis under the supervision of Kapranov. And there are also more recent references which give this. Yes. And so back to the question about derived algebraic geometry. Yes, I mean, A infinity algebras and A infinity categories. Yes, since if we look at them up to quasi-isomorphism, they are the same as DG algebras and DG categories. And there is a branch of mathematics known as one version of non-commutative algebraic geometry, which is based on DG categories, and which you could equally well base on A infinity categories. And but it's a non-commutative, it's non-commutative algebraic geometry. So yes, so it's a long story. I gave a series of lectures about this in July and September in Tsinghua. So if you look for for my course at Tsinghua, you can get a lot more information about this.
Thank you very much for answering all the questions and for the talk. Then maybe we can think it again, and we can have a break of 1 or 2 minutes and start the next talk.
Okay, hi. Yes, I'll just be away for 2 minutes and then come back. Okay.
And if you need more, then please.
Okay, just a second. Yeah, thank you.
Thanks. Yeah.
Are you making one recording of the 2 talks together, or?
Yeah, so that's what I was wondering. Maybe I will stop this one and then
maybe
see
to make two.
to have the 2 separate videos, but I've never done that before. So
I think you can just stop it and then
okay,
start a new one.